Hi everyone. In this course, I'll be sharing my knowledge on safety aspects in different radiological modalities. Diagnostic radiology involved various modalities including X-ray, mammography, interventional radiology, MRI. All this imaging modality we can able to discuss here and share the knowledge on the safety aspects of it. Thank you and welcome you all into this course. A very good day to one and all. Today we will be discussing about foundations of radiation safety. First of all, we have to know what is the principles of radiation protection. There are three philosophy of radiation protection which involves justification, optimization and dose limits. So radiation protection aims to reduce the radiation risk while achieving diagnostic benefit through justification, optimization and following the ALARA principle. Justification. What is justification? Any investigation that we are performing, that should have a positive benefit, that should always outweigh the risk of that particular examination. Even though while we are doing a chest x-ray, it should have a positive benefit. So that is what no radiological examination should be performed unless it provides net benefit to the patient. The diagnostic benefits must outweigh the radiation risk, as ionizing radiation has no safer threshold. Even you can't tell that minute radiation, there is no threshold. Even a minute radiation can cause the biological risk to that particular individual. So an examination is justified only if it influences diagnosis or patient management. So the referring physician decides justification while the radiologist and radiographer ensure the correct examination and avoid unnecessary repeated examination. And also while performing any CT investigation, you can avoid various phases. Only necessary phases you can acquire and reduce unnecessary repeated radiographs. The second philosophy of radiation protection is nothing but optimization. Optimization is nothing but you have to optimize the radiation dose. It is not about giving an excessive dose and producing a high quality image. You have to get, it aims to achieve a good quality image with a minimum exposure. How much ever lesser radiation that you can able to give, that you can give and get an optimized optimum quality image. Proper technique, you have to use proper positioning, and also exposure factors are essential, and prevent unnecessary repeated examination. This optimization means using the lowest radiation dose that produce diagnostically acceptable image. When we move on to the third philosophy of radiation protection, that is nothing but dose limit, that we must follow the ALARA principle, as low as reasonably achievable. As we know, the ALARA is based on the concept that no radiation dose is completely safe. Even a minute radiation that can create a damage in biological tissue. Also, this ALARA principle is accepted by all the regulatory authority. If you consider India, Atomic Energy Regulatory Body, and International Commission on Radiation Protection, ICRB, and all the national and international regulatory authorities have been accepted this ALARA principle. It is implemented using the three cardinal principle, that is nothing but time, distance and shielding. What is time? Time is nothing but the exposure time. If you consider the fluoroscopic room, we are doing the continuous fluoro. So the time of exposure, continuously if you are exposing, then the radiation risk is higher, isn't it? So the time of exposure should be restricted. Nowadays in modern machines, you can see that the time after exceeding every 5 minutes, there is an alarm that reminds you that you are exceeding the limit. So the time of exposure should be reduced. Also, you have to reduce the time that you are staying in the radiation field. As a technologist or as an interventional radiologist, that we have to reduce the time that staying near the radiation field. Also the distance, we have to make a far distance from the radiation beam or primary radiation beam. That means that you have to follow the inverse square law. That means as the distance increases, the intensity decreases. That is inversely proportional. So double the distance, 1/4 will be the intensity. triple the distance, 1 by 9, and 4 times if you increase the distance, 1 by 16, it will reduce the intensity of the radiation. So always maintain that distance, and also use appropriate shieldings while performing the radiological investigation. Anyway, there is particular barriers, primary and secondary barriers are there. Use control booth. Behind the control booth you have to expose, and all the accessories, lead shieldings, lead aprons, thyroid shield, lead goggles, all the equipment, gonadal shielding, all the equipments and devices which is available that you can utilize for yourself as a technologist as well as for the patient wherever it is applicable. The next section is for radiation units and dose quantities. So radiation units are the standardized measurements used to quantify radiation exposure, dose and biological effects on patients and the individuals. So the first one is exposure. Exposure is nothing but it is the measures. It measures the ionization produced by an X-ray or gamma rays in air only. So its unit is coulomb per kilogram, and traditional unit was Roentgen. And air karma is nothing but it is the kinetic energy released per unit mass of air by radiation. Its unit is gray, and the absorbed dose is nothing but it is the amount of radiation energy absorbed per unit mass of tissue. So its unit is also gray. The traditional unit is rad. 1 gray is equal to 1 joule per kilogram, and you can convert that 1 gray is equal to 100 rad. The next one is equivalent dose. Equivalent dose is the dose accounts for different biological effectiveness of different radiation. So equivalent dose, the formula is nothing but equivalent dose is equal to absorbed dose into radiation weighing factor. You can see in the right hand side the type of radiation, that is X-ray is 1, gamma rays it is 1, and if you come down, fast neutron and alpha particle is respectively 10 and 20, and slow neutrons it is 5. So radiation weighing factor will vary. So the equivalent dose is nothing but the absorbed dose into radiation weighing factor. So the radiation risk, the biological risk is more in alpha particle compared to X-rays and gamma rays, and more in fast neutrons compared to X-rays, gamma rays and beta particles. So the unit is sievert and the traditional unit is RAM. The effective dose is nothing but it considers both radiation type and tissue sensitivity. The effective dose formula is nothing but the equivalent dose into tissue weighing factor. Equivalent dose formula, we know that absorbed dose into radiation weighing factor into tissue weighing factor. So the tissue weighing factor for different tissues, the tissue weighing factors is changing. Skin you can see 0.01, bone surface it is also 0.01, and bone marrow, red bone marrow it is 0.12, colon it is 0.12, bladder it is 0.04. So this will vary according to different organ and tissues. So effective dose consider both radiation type and tissue sensitivity. The formula is nothing but absorbed dose into radiation weighing factor into tissue weighing factor. And there is another one, collective effective dose. Collective effective dose will calculate when there is a radiation accident or incident which is happening for a population, for a particular area. That is nothing but the average effective dose in that group we will take. The average effective dose in that group into number of people in that particular group. That is the calculation for collective effective dose. Any kind of radiation accident which is happening in a population, we will use this collective effective dose. So we can get the overall radiation exposure, and its unit is man-sievert. And also we have dose area product. DAP is the total radiation energy delivered to the patient surface. DAP is the formula is nothing but air karma into the area, So unit is milligray centimeter square. Here we have two CT dose quantities, CT dose descriptors, nothing but CTDA volume and also dose length product. One is for CT scan volume and the other one is for CT scan length. So CTDA volume is the average absorbed dose in a CT scan volume, which is represent dose per slice in a CT, and displayed on a CT console automatically. You can see the unit is milligray. So this CTDA volume and DLP, dose length product, we are particularly using for DRL, diagnostic reference level. To establish diagnostic reference level, you can use this two dose descriptors. The second one is dose length product. DLP is the total dose from the entire CT scan length. So DLP, the equation is CTDA volume into scan length. So indicates total patient dose from a CT scans. So its unit is milligray centimeter. So that's all about radiation quantities and radiation units and dose quantities. Also about the basics of radiation protection. See you in the next session.